Yes?
No, yeah. Wait a minute. Soumya, you can start maybe.
Okay, great. All right. So thank you everyone for coming. We are now going to start our talk. Today we have Masha Vlasenko from IMPAN Warsaw talking about cohomology and congruences.
Hello. Thank you very much to inviting me to Pascacharya Pratishtana. I think
The
this
voice
is
is a bit little weak, maybe you can speak louder.
yes. Do you hear me now?
Yeah, it is little bit better.
Okay. Yes.
Now it is coming good.
So thank you for the invitation. I'm going to give 2 lectures. The first one will be in general about cohomology and congruences, and the second one will be applications to Calabi-Yau varieties and mirror symmetry. This is joint work with Frits Beukers, and today's talk is based on a series of our papers called Dwork crystals 1, 2, and 3. The first 2 are published in the International Mathematical Research Notices, and the third one is submitted. Okay, so I will start with some elementary congruences, which were observed by Dwork, and the story goes back to his proof of rationality of zeta functions and also deformation theory of zeta functions. But mod P, these congruences are usually older. So first, let me show you some congruences for constant terms of powers of a Laurent polynomial. Do you see my pointer on the screen?
Yes.
Thank you. Okay, so here G is a Laurent polynomial. This is a finite sum of monomials. X to the u means x1 to the power u1 times x2 to the power u2 and so on until xn to the power un. And gu are integral coefficients. This is a finite sum. The support of G is the set of vectors, the set of exponent vectors of monomials present in G. And the Newton polytope of G is the convex hull of the support of G in the n-dimensional space. This is a convex lattice polytope. Let's consider the sequence of constant terms of powers of our Laurent polynomial. Here is an example. If the Laurent polynomial is x1 plus x2 plus 1 over x1 over x2, then our sequence has zeros when 3 does not divide k, and otherwise it's k factorial over k over 3 factorial cubed. So here is a property of such sequences of constant terms. The notation is as in the previous slides here, but we require that the interior of the Newton polytope has only one integral point, and this point is the origin. In the previous example, we had this Newton polytope, and this is the case when it has only one interior integral point, which is the origin. So the above sequences will have this property. And the property is as follows. For any prime number p, we have the following congruence, where ckI, so ki's are digits of the p-adic expansion of k. For any integer k, we write it p-adically. We have digits between 0 and p minus 1. And then ck, the respective constant term, is congruent to the product of ck's modulo p. That is, the sequence of constant terms is determined completely by the first p terms from C0 to Cp minus 1. This is called Lucas congruence, congruence, and it was discovered on binomial coefficients. Lucas theorem is a similar property for binomial coefficients. Next, let me show you a generalization of Lucas congruence modulo p to the s for various s. This is called Dwork's congruence. Let gamma of t be the generating series of the sequence of constant terms. Note that this sequence can be written as the following integral. Here we expand 1 over 1 minus t times g as a geometric series, the sum of t to the k, g to the k, and then apply Cauchy's theorem and get the sum of c, k, t to the k. This may not be directly related to the story of congruences yet, but it will be used in their proof, in the proof that I will show. And for those who know about period functions, we see that this gamma of t is a period function for the family of varieties defined by equation 1 equals to t times g, the family of hypersurfaces of zeros of these polynomials here. The condition in which we are working, that the Newton polytope has a unique internal integral point, then is related to the fact that these hypersurfaces can be compactified to Calabi-Yau varieties. If we require more from the Newton polytope, this property of the Newton polytope is called reflexivity. But now we are working in the conditions of Lucas congruences. And we also consider truncations of the generating series, so partial sums. They are denoted by gamma m, the sum of m for first terms of this series. Then, under the assumptions as before, that 0 is the only internal integral point in the Newton polytope of G, for any prime number p and any integer s, we have the following congruence modulo p to the s. So how can we look at this? First, note that the generating series gamma of t starts with the term 1. C0 is the constant term of g to the 0, which is 1. So C0 is 1. And therefore, 1 divided by gamma is also a power series with integral coefficients. And this ratio here is a power series in t with integral coefficients. The same is true on the other side. It's a power series in t with integral coefficients. So we are saying that each coefficient is congruent to each coefficient modulo p to the s. This is the meaning of what is written here. Also, let's note that it means that this power series on the left, the ratio, is approximated by rational functions, because here this is a ratio of two polynomials. Such functions, which can be approximated p-adically by rational functions, are called p-adic analytic elements, or p-adic analytic functions, or rigid functions. So this theorem gives an explicit p-adic approximation to the ratio of our function divided by our function to t to the p. If we put s equals 1 here, then the denominator on the right side is just 1. And we have the sum of first p terms in the numerator here. And one can easily see that this is precisely the Lucas congruence for the coefficients ck. So when S equals 1, Dwork's congruences become lookup congruence, but here we have them for all powers of P. And the proof that we gave with Anton Mellet in 2013 was combinatorial. And later we thought a lot about what is the reason for this congruence. The proof somehow was not satisfactory. And together with Frits, we found some explanation to this, which has other applications. It turned out to be a very fruitful result. But the starting point was basically this. And we were able to reprove this theorem using a new method, which I'm going to present today. And also we noted during this proof that the ratio, the same ratio, gamma of t or gamma of t to the p, can be approximated p-adically by rational functions with only powers of gamma p, the truncation of first p terms in the denominator. So I wrote it here as the second theorem that under the same assumptions, our ratio can be approximated by, belongs to the p-adic completion of the ring, localization of the ring of polynomials by this polynomial gamma p. Okay, so now I want to show you another elementary congruence of different kind, which we'll prove using the same methods, and then later we'll start proving both of them. So this congruence concerns expansion coefficients of rational functions. So let me introduce formal expansion of rational functions. We again start with the Laurent polynomial in n variables. Delta is its Newton polytope. Take another Laurent polynomial, take an integer m greater or equal 1, and consider the rational functions, function h divided by f of x to the m. Then to do the formal expansion, we pick a vertex of the Newton polytope of f. There will be a different expansion for every vertex. So let this vertex be b. What we do, we take the term fb x to the b out of the expression for f. So this one here corresponds to taking the term out of the bracket, and L are all other monomials divided by this term. In particular, this Laurent polynomial L here will be supported in, if this is delta, then L is supported in the shift of delta by b, delta minus b. So b is moved to 0. What we do next, we apply the geometric series, we do the formal expansion of this term, 1 plus L to the power minus m. These are some ratios of factorials. They can be written through binomial coefficients with positive, I think, m plus m minus 1 plus s. Choose s, or something like that. But note that here, all terms are powers of L, so they are supported in the positive quant spanned by this delta minus b, by the shifted Newton polytope. So the expansion here is supported in this con. All terms are supported in the con. And secondly, there are finitely many contributions to every monomial in the con. This is because L actually has no 0 term. It's supported in this shifted polytope, but without the 0. So when we take powers of L, they move higher and higher. Their support moves higher and higher in the con. Okay, and then we just multiply by finitely many monomials here. So the result is a sum over all vectors in D to the n, some with coefficients in the in the localization of z by this coefficient fb. It is supported in the finite union of shifts of this cone. And let me note that in this procedure of formal expansion, if the numerator is supported in m delta, then here we have a Laurent polynomial, which is supported in the same cone on delta minus b, because we divided h by x to the mb. And functions supported in the cone, they form a ring. We can multiply them. So then, in this case, the whole expansion will be supported in the cone on delta minus b. We will use this fact later. Okay, so here is the congruence that I wanted to show. It's called Gauss Congruence. We take f with Newton polytope delta as before. We consider a rational function and do its formal expansion at a vertex b, just as in the previous slide. Then, assuming that delta has a special property that the only integral points in delta are vertices. For example, the unit cube will have this property. Its only integral points are vertices. So under this assumption, and assuming that h is supported in delta, so in particular, the thing here is supported in the cone on delta minus the vertex b, then for all primes which do not divide the coefficients of f, we have the following congruences for the expansion coefficients. Namely, for every vector in the cone, v, the respective coefficient at v, is congruent to the coefficient at v divided by p to some power of p. And this power of p is the minimal power which divides all coordinates of the vector v. This was proved by Frits and collaborators in 2018, but again, the method that we developed also applies to this congruence and sort of explains it. So let's start the explanation. I'm going to introduce some setup in which we will work. So we're coming to cohomology. Let f be a Laurent polynomial with coefficients in a ring of characteristic 0, ring R. xf denotes the hypersurface of zeros of f in the n-dimensional torus. And delta denotes the Newton polytope of f. We consider a ring of rational functions having only powers of f in the denominator. The numerators are with coefficients in the ring R. And we also assume that for h divided by f to the m, the h is supported in m delta. So these are regular functions in the sense of algebraic geometry on the complement of the hypersurface of zeros, xf. But not all regular functions, because we have this bound on the support. And we look at this, this set, omega f, as an R module, because we can add elements here. We will also need a submodule consisting of derivatives, partial derivatives in the coordinates x1, xn of the elements of omega f. One can quickly check that logarithmic derivatives xi times d over dxi preserve this shape. So they act from omega f to omega f. And we consider the R module generated by images of partial derivatives. Let me remark that the quotient of the module of rational functions by the module of derivatives is isomorphic to the middle Theorem cohomology of the complement of the hypersurface of zeros. This was proved by Griffiths and Battery. And this is true under certain conditions, namely when F is delta regular and R is a field. And delta regularity means smoothness of the hypersurface XF. But moreover, there is a way to compactify it in the projective variety attached to the Newton polytope, and all components of this compactification are required to be smooth. So this is a strong condition. We are not going to use it. We will work with the quotient module here, and just remember that sometimes it's equal to Theorem cohomology, but we are in a more general situation. We can consider any Laurent polynomials and do not require any smoothness conditions. This isomorphism goes as follows. The rational function corresponds to this rational function times the differential form, the product of dxi over xi. And then it's clear that the module of derivatives corresponds to exact forms. So more or less the arrow in this way is easy to see. And also let me mention that if we consider filtration on the module omega f by the order of pole, so when m here is less or equal than something, this is an increasing filtration. It corresponds to the Hodge filtration under this isomorphism with the middle Theorem cohomology. We will use this filtration. Okay, so now I would like to introduce a p-adic operation on our functions or respective differential forms. We pick a prime p and assume that our module is that the ring R is separated in p-adic topology. That is, the intersection of all powers of the ideal P is 0. Under this condition, we can introduce the p-adic topology on R. And consider the following operation, which takes a rational function, takes its formal expansion at a vertex B, and then removes the terms which have exponents not divisible by p and extracts the p's root afterwards. So this is the operation. It's quite clear that we are destroying the fact that it's a rational function. We do some weird operation with the formal expansion here. But we can remedy this problem in the following way. For that, we need to consider Frobenius lift on R. Frobenius lift is a ring endomorphism such that sigma of R is congruent to R to the P modulo P for every element R. Examples of Frobenius lifts are the identity, the trivial lift on the ring Z, because of little Fermat's theorem. On the ring of polynomials Z of T, we can take the operation which raises the variable to the power P, the variable in the polynomial. Again, by Fermat's little theorem, this will be a Frobenius lift. Okay, so assume that we have a Frobenius lift on the ring R. Then it turns out that after we apply the Cartier operation to the formal expansion of a rational function with powers of f in the denominator, the result can be approximated p-adically by rational functions with powers of f sigma in the denominator, where f sigma is f with sigma applied to its coefficients. By this lemma, we have it that the image of our module omega f is in the p-adic completion of the module omega f sigma. So performing these operations leads us out of the ring of the module omega f, but it is well defined on p-adic completions. we can extend it by linearity to p-adic completion of omega f. And we have an R-linear operation from omega f, or from the p-adic completion of omega f to the p-adic completion of omega f sigma, which is given by this simple formula on formal expansions. It turns out that this operation is independent on the choice of the vertex B. So for every vertex, when we perform this thing, it reduces to the same operation on the p-adic completions of modules of rational functions. The second property is that it descends to the quotient by derivatives. Namely, if we look at commutation with partial derivatives in the variables xi, there is a p-commutation relation. So if we apply Cartier operation to a derivative, it will be p times the derivative. I could put p here. In particular, we have an operation on the quotients. And the last property I want to mention is when the rank of coefficients is Zp, then traces of powers of the Cartier operation count points over finite fields on the complement on the hypersurface of zeros of f. So somehow this is an example of a point counting operation, like Frobenius operation. Okay. So with the use of this Cartier operation, we were able to prove the following result, which will be the key to the congruences, the key fact to improving the congruences we started with. We introduced the Hasselbait matrix. It's a matrix indexed by pairs of integral points in the Newton polytope delta, and it treats the respective coefficients in the p minus first power of the polynomial f. Here h is the number of integral points in delta, so this is an h by h matrix with coefficients in R. If we assume that R is p-adically complete and this Hasselbait matrix is invertible, by the way, this is equivalent to the fact that P does not divide the determinant of the Hasselbait matrix because we assume that R is p-adically complete. And if R was not p-adically complete, we can complete it at this point. So basically the requirement is that P does not divide the determinant of the Hasselbait matrix. In this case, the quotient of our module by formal derivatives, I will explain in a moment what it is, by certain submodule, is a free module of rank H, where the basis is given by the images of rational functions x to the u over f of x, with u running over integral points in the Newton polytope delta. So this is a finiteness result, sort of finiteness of cohomology result, which does not assume smoothness of the hypersurface, but this Hasselbait, the p-adic Hasselbait condition is required. Now let me explain what are formal derivatives. Formal derivatives are larger than the usual derivatives, d omega f, which were introduced here earlier. So the thing here is a quotient module of the cohomology module, omega f divided by d omega f. Formal derivatives are defined as rational functions whose formal expansions, we fix some vertex b for that of the Newton polytope. So we look at rational functions whose formal expansions have the following congruence property, that for every u, the coefficient iau is divisible by the greatest common divisor of the coordinates. It's clear that partial derivatives, partial logarithmic derivatives of power series will have this property. Because when we apply this the coefficient is multiplied by ui, right? And then the odd linear combinations will be divisible by the greatest common divisor. So we can say that we see that the usual derivatives will have this congruence property, but now we're looking at those functions which can be integrated as formal series, not necessarily as rational functions. So they are formal derivatives. They can be integrated as formal series. And also we can define this module using the Cartier operation. Since R is p-adically complete, it's a ZP algebra, and therefore only powers of P matter because all other primes are invertible in R. Only powers of P matter for this divisibility. And in particular, this property will hold if for every S, application of the Cartier operation S times gives us an element, an expansion, which is divisible by P to the S. This later reformulation also shows that this submodule is independent of the choice of the formal expansion vertex B, if we believe that the Cartier operation is independent. This is a curious property here. Okay, note that the Cartier operation applied to formal derivatives gives P times a formal derivative. Therefore, it's because of this congruence property precisely. So there will be a formal derivative divisible by P. In particular, the Cartier operation descends to the quotients of our module of rational functions by formal derivatives. And assuming the Hasselbait condition, these are free quotients with a canonical basis given here. So we can ask about the matrix of this operation in the two canonical bases. In the next slides, I'm going to speak about determining this matrix. It turns out to have interesting entries. And note that if we started with a ring R, which was not p-adically complete, for example, we worked with Laurent polynomials with coefficients in Z, then at this point, we have it p-adically complete. So Z turns out to be ZP, and the coefficients of this matrix are elements in the p-adic completion. Okay, so let lambda be the matrix of the Cartier operation in the two bases from our theorem. This is the definition of this matrix. And now we pick any vector in the cone in which the formal expansions are done, and rate expansion coefficients at powers of P times this vector in the above identity. Due to the definition of formal derivatives, the result here will be divisible by P to the S. Here we get the following thing. So if we define vector alpha S indexed by integral points in delta as coefficients at x to the power P to the S W in x to the V divided by F, then these vectors satisfy the following congruences modulo P to the S. Alpha S is congruent to lambda times alpha S minus 1, sigma applied to alpha S minus 1. Frobenius lift applied here. In fact, this gives us a way to approximate the entries of lambda by expansion coefficients. Because if we find a proper set of vectors W, this alpha here depends on the choice of W. We are reading coefficients along some line in the cone. So if we pick a good subset of lines, H lines, then so that these matrices are invertible, then lambda will be congruent to the matrix times S matrix times the previous S minus first matrix with the Frobenius lift applied on this side. And this will be a p-adic approximation to the entries of lambda. This principle will give all the congruences which were introduced earlier. Here is the Gauss congruence. So we are considering expansion coefficients this should have been h of x divided by f here. So I start with a Laurent polynomial f with integral coefficients whose Newton polytope has the property that the only integral points are vertices, like the unit cube, for example. And pick a prime which does not divide any of the coefficients of f. In this case, the Cartier operation turns out to be the identity on the quotient by formal derivatives. So our matrix lambda will be the identity matrix. And therefore, for any rational function, here it should be h, not just x to the v, the coefficients satisfy this Gauss congruence because lambda is the identity matrix. It's just the congruence from the previous slide where lambda is absent. To prove Dwork's congruences, we need a version of our key theorem, which is the following. We consider subsets of the Newton polytope. A subset is called open if its complement is a union of faces of different dimension. Here are examples of open subsets. So we can, for example, this is a two-dimensional polytope, and we can remove all faces of dimension 1. Here we remove two faces of dimension 1. We can also remove vertices, faces of dimension 0. Here is the polytope with two vertices removed. All these are open sets in our sense. This is a finite topology on delta. Okay, it turns out, and quite easy to check, that the following submodules are denoted by omega f mu, where we require that the numerator is supported in m mu instead of m delta. That these submodules are preserved by the Cartier operation in the following sense. Omega f mu is mapped to omega f sigma mu. I mean, p-adic completions. If the Hasselbait submatrix corresponding to the subset mu is invertible, by that we mean that in beta p entries are indexed by integral points in delta. So now we only leave those points which are in mu. On these pictures, we have integral points in mu. If that submatrix is invertible in R, then we have the similar result, that the quotient is finite and rational functions with support in mu, with denominators supported in mu, represent the quotient. With this, we can do Dwork's congruences. So we start with a Laurent polynomial G, whose Newton polytope has a unique internal integral point, and this point is the origin. Consider the generating series of constant terms of powers of G. Take the Laurent polynomial given by 1 minus tg, where t is the new variable. This variable will go to the ring R, so our ring R should contain polynomials in T. Choose mu to be the topological interior of delta, like here. So the only integral point in mu is 0. Therefore, the Hasselbait submatrix is 1 by 1, and this is the constant term of 1 minus tg to the power p minus 1. Its expression is written here through constant terms of powers and some binomial coefficients. And if we take a ring which is p-adically complete and in which this polynomial of degree at most p minus 1 is invertible, well, the minimal such ring is written here. we invert this Laurent polynomial and take the p-adic completion. Then over this ring, the quotient by formal derivatives will be of rank 1. And then it turns out that the respective 1-by-1 Cartier matrix, the matrix lambda, is precisely the quotient that the Dwork's congruences are about. In particular, we see that this quotient belongs to the ring, this ring. So it can be approximated p-adically by rational functions with beta p in the denominator. Dwork's congruences in the form that this is congruent to some ratio of truncations can be proved by using this idea alpha s is congruent to lambda times alpha s minus 1. So we just have to pick a proper linear combination of expansion coefficients of 1 over f to get the congruence. And let me also note that this beta p modulo p is congruent to the truncation gamma p, because here this is congruent to 1 modulo p. And therefore the ring where gamma p is inverted and the ring where beta p is inverted will have the same p-adic completion. This is an easy lemma to check. So in particular here we could say that this ratio can be approximated by rational functions with the powers of the truncations of the truncation of the first p terms in the denominator. This was our second theorem on the slide about Dwork's congruence. Okay, and after showing congruences and their cohomological proofs, I want to switch to a topic of supercongruences. To explain this, I start with a generalization of the key theorem, which was shown in the first part of the talk. This is a theorem about the quotient by formal derivatives. So now we have the following generalization. For any number integer k, and we assume that k is less than p, so I choose a big prime or fix a prime and choose a smaller number k, we have something called the case Hasselbait determinant, which is similar to the first Hasselbait determinant introduced previously, but I don't want to write it down. If that determinant is not divisible by p, then we have the following decomposition of R modules, where this is a free module generated by functions x to the u divided by f of x to the k, where u is supported in k delta. This is a free module of rank how many integral points are there in k delta. And fk is the module of formal k partial derivatives. It can be defined through congruences again. So fk consists of rational functions in whose formal expansions have coefficients divisible by the k's power of the GCD of u1, un. Or we can define it through the Cartier operation. Now there is a divisibility by p to the power k as here. This condition is stronger than the condition for formal derivatives, which was the case k equals 1. So this is the decreasing filtration. When we increase k, the requirements are stronger. And then one can prove again that this divisibility condition is equivalent to being generated by k's partial derivatives. All right. So with this theorem, we can do the following. Let's look, first, let me say that we can apply the same idea. We can quotient by k's formal derivatives and compute the matrix of the Cartier operation, because Cartier operation sends k's formal derivatives to k's formal derivatives. So this idea of congruences applies, but now they will be congruences modulo p to the power ks. Let's look at this in the following example. Here is a Laurent polynomial in 2 variables, and t is a variable in the ring R, which we will assume to be the p-adic completion of the ring of Laurent polynomials in T. Then, modulo the first step in this filtration, we have that Cartier operation sends 1 over f to 1 over f sigma, whatever choice of sigma is the Frobenius lift. It could be just sending t to the power t to the p or some other function here, a p-adic analytic function, which is congruent to t to the p modulo p. But if I look modulo the second step in the filtration, we have the following refinement of this formula, where a derivative of 1 over f appears, the logarithmic derivative. What we note here, so this log is defined formally in the power series because t sigma over t to the p is congruent to 1 modulo p. This will be a well-defined element of the ring R. We note from this formula that t sigma equals to t to the p will be the Frobenius lift for which this term is 0. This lift is special because it means that this congruence is preserved even modulo p square f2, the second step in the filtration. This is a special lift for which this congruence is modulo a smaller submodule. This idea comes again from Dwork's work. We will see more examples in the next slides. And such Frobenius lifts are called excellent. Note that for the excellent Frobenius lift, for this one, which is t sigma equals to t to the p, we have the following supercongruences for expansion coefficients of 1 over f. So if this is the formal expansion of 1 over f, which is now supported in the first quadrant, because we expand b equals 0 here, the vertex of delta. Delta is the unit square, and we expanded 0. But we could expand it any other vertex too. So these expansion coefficients satisfy the following supercongruences. In this, why do we call them supercongruences? You see 2 times the p-adic order of v here. If we only had this congruence modulo f1, or there is p times f1, which is a technical difference, but from this congruence, with any Frobenius lift sigma, this congruence would be true modulo p to the power p-adic order of v without the 2, and with any t sigma here. But for the special lift, t sigma equal to t to the p, we have a 2 here. So this becomes stronger. And there are many examples of such things in the literature, when the congruence, which is usually modulo p to the s, becomes for all s, becomes a congruence modulo p to the 2s or 3s and so on suddenly because of some special property. So here this property is the special Frobenius lift, which is called the excellent lift. The last thing I want to do is in this lecture, I want to consider a more sophisticated example of Dwork's families and determine the excellent lifts for these families. Here are Laurent polynomials we want to consider. This is in R variables, and T is again a parameter which belongs to the ring R. We assume that P does not divide 2 times R plus 1, and under this condition, there exist 2 functions, lambda 0 and lambda 1, p-adic power series, such that CP, the Cartier operation applied to 1 over f, is a linear combination, lambda 0 times 1 over f sigma plus lambda 1 times the derivative of 1 over f with the Frobenius lift applied. Theta is the logarithmic derivative in t. This is a result of some computations using our main theorem and along the lines explained in the talk. But lambda 0 and lambda 1 here are they come from our theory. We don't know what they are explicitly, but actually we can work them out as in the previous example. Just it's more complicated, and this is what we're going to do. These functions depend on the Frobenius lift, both of them. And we would like to determine such Frobenius lifts, excellent lifts, for which lambda 1 will vanish. So again, 1 over f will be an eigenvector modulo the next step in our filtration by case formal derivatives. To give the answer to what excellent lifts are for Dwork families, we have to consider the differential operator of order R, which annihilates 1 over f in the sense that the result of application of this operator to 1 over f belongs to the submodulo of derivatives. These are called Picard-Fuchs differential operators. They represent the Gauss-Manin connection in algebraic geometry under that isomorphism with Theorem cohomology. In this case, if we consider the submodule omega f delta naught, the interior of delta, and divided by derivatives, we will get a cyclic theta modulo of rank R. So this is a differential module with this differential operator. I mean, it's a cyclic module generated by 1 over f, and 1 over f satisfies this differential equation. L of 1 over f is 0 in this quotient module. Here we wrote the smallest rank R over which this isomorphism is true. We look at the solutions to our differential operator L. There is a power series solution, which comes with a sequence of constant terms of powers of f. Of this one. We called it g of x before the polynomial here. So this is these are constant terms of powers of the polynomial in R variables here. It's just as in our first example, but now we have R variables. After the rescaling of like t to the power r plus 1 is some new variable, this is a hypergeometric function actually. And I wrote this formula, this Cauchy formula again, to see that how this Picard-Fuchs differential operator annihilates the respective form in the middle cohomology of the complement of the hypersurface. Anyway, there is a power series solution, and there is the only one, because this differential operator has local exponent 0, 0, 0 at t equals 0, and its monodromy is maximally unipotent. So there will be no other power series solutions, but there will be a log solution. So log t times the first solution plus a power series. And if we require that this power series has 0th constant term, then it's unique of this shape. And one can continue solving and find a basis in the space of solutions consisting of polynomials in the log of t with power series as coefficients. This is some standard procedure of solving differential equations near regular singular points. But we will only need the first two, the power series solution and the log solution. The formal series denoted by q of t, which is the exponent of y1 divided by y0, or if we divide this by y0, there will be log of t plus g over y0. So the result is t times the exponent of this series starting in degree at least 1. So this is a formal series whose term in degree 1 is t. This is called the canonical coordinate. So here is the, in this slide, I'm going to present the answer on what the excellent lifts are. So I just remind you that we have this Picard-Fuchs differential operator, and we have two solutions to it, y0 and y1, and the canonical coordinate q. Then when p does not divide 2r plus 1, firstly, the canonical coordinate is p integral for every p that does not divide 2r plus 1. Note that the canonical coordinate has no p in its definition. So this is a statement that actually the canonical coordinate can only have primes in the denominators of coefficients which divide 2r plus 1. It's p integral for almost all primes p. Under this condition, like if we assume that this is true, note that T can be expressed as a power series in Q, also with p integral coefficients, the inverse series. It's called the mirror map. I will speak about canonical coordinates and mirror maps in the context of mirror symmetry next time. Now these are just some names. So both T and Q can be the generators of our ring. And the next statement is that the excellent Frobenius lift sigma is given by raising q to the power p. We sort of found the coordinate for which the excellent lift is given by raising to the power p. And this turns out to be the canonical coordinate determined by the Picard-Fuchs equation. Now, how does this lift looks like in terms of t? What is T sigma? So how to apply this sigma to T? We consider T as a power series in Q, raise Q to the power P, and then substitute Q as a series of T and get T sigma as a series in T. The last part of the theorem is about this function. T sigma is a function of T. It's congruent to T to the P modulo P because it's a Frobenius lift. It turns out that this function is a p-adic analytic element. Moreover, we can specify the rational functions, the denominators of the rational functions, which approximate this function. It can be approximated p-adically by rational functions with the first and second Hasselbait determinants in the denominator. Hasselbait determinants are determinants of Hasselbait matrices which enter our main theorem about supercongruences. I didn't write down the second Hasselbait determinant, but you have seen the first Hasselbait determinant in the first theorem, which I called key theorem. And they are polynomials here. So really, this is an approximation by rational functions. And finally, if we look at the case of r equals 2, this can be compactified to a family of elliptic curves. And therefore, it's no surprise that T as a function of the canonical coordinate is a modular function. Now it's of level 3. In the last part of his paper on p-adic cycles, Dwork considers the J invariant function and the expression of J of Q to the P as a function of J. He proves that this function, f here, is a p-adic analytic function with fixed denominators. Here, B1 to BR are p-adic representatives of J invariants of supersingular elliptic curves in characteristic P. So basically, this function f can be approximated by rational functions with the polynomials in the denominator whose roots are the J invariants of supersingular elliptic curves. He proves it using the algebraic relation between J of Q and J of Q to the P. And also he proves a similar thing for the modulus lambda, which corresponds to the Legendre family of elliptic curves. If you look at our theorem from the previous slides, of which this is a particular case here, then polynomial the first Hasselbait polynomial corresponds to supersingular fibers of the family. And the last part of the theorem is a generalization of Dwork's results, which goes beyond modularity. For r greater or equal 4, our families are not modular. Differential operators are not modular. And the outcome is that in the general case, we just have to add the second Hasselbait polynomial to approximate these excellent lifts as rational functions. Thank you very much for your attention.
All right, thank you, Masha. Let's thank the speaker. Are there any questions?
So Masha, what's the supercongruence looking like for your last example?
Let's see my first example. 1 second. Do you mean the this one, the modular example?
Yeah. So using your excellent lift, right? You get to the
yes.
T to the 2x. Yeah.
Yes. Okay. So the supercongruence in this case is we look at the hypergeometric function divided by the hypergeometric function of t to the p. Okay. Usual Dwork's congruences will tell us that this is congruent to some ratio of truncations. And we were actually trying to find, like, if we use the excellent Frobenius lift, would that be true modulo p to the 2s?
Yeah.
And I think Frits did experiments in which it was true, but somehow not always that we truncate first p to the s terms, but we need to truncate 2 times p to the s terms. So, in this case, but we were not able to prove this. It is just experimental. In our paper Dwork crystals 3, there are some conjectures about supercongruences. But this is when we want to prove something about truncations. In principle, supercongruences are here always, and they look like, let me show you the source of supercongruences. Okay, this is this slide, the blue part. If we work modulo at higher steps in the filtration, fk, this is f1 in our new notation, there would be modulo p to the power ks. But the problem is that the matrices, I mean, here alphas are vectors, but they said that if we pick sufficiently many such vectors, we can make them into matrices. When k is 1, these matrices can be made invertible, and we really get the approximation to lambda. When we are at supercongruences, the matrices are not invertible modulo p. But still, some part of this linear algebra can be done, but it becomes more complicated.
Okay. Thank you. A very nice talk. Thank you.
Thank you.
There are other questions.
Because you are assuming that the Hasselbait matrix is invertible, so at P. So that means you are considering the case P rank is H, right?
Yes.
So your supercongruences, you are not assuming that you are considering a super singularity. So I going to super singular fibers. I don't know what is happening for supercongruences.
In the theorem about supercongruences, there were Hasselbait conditions. Certain determinants are invertible.
Yeah.
But what that means is that the determinant of the Cartier action modulo p to the k is divisible by as small power of p as possible.
Yeah.
But still, that power is non-zero. We can count it. There is a way to count it using the Newton polytope, the number of internal points.
So the Hasselbait is not invertible then?
Well, it depends. We have a definition of Hasselbait determinants, which should be invertible, but they are not exactly determinants of the this Cartier matrix modulo p to the k. The definition is more sophisticated. Okay, these are certain subquotients, and they're divided by the proper power of p, Cartier operation becomes invertible.
Okay. Okay.
So it's not so easy as the congruence on the screen.
Yeah. So passing it to supercongruence, we skipped a little bit. So okay.
Yes. So we sort of lose some powers of p in the supercongruences if we want to invert. But still, doing something is possible. For example, in the next talk, we will exploit supercongruences. We will work modulo higher steps in our filtration to get information about Calabi-Yau differential operators.
Okay, so in the next talk, you probably will do the integrality of this mirror maps.
Yes, and we can do it.
So the 14 families, hypergeometric families, probably you cover that?
I think we can do some of them, but maybe not all of them. We didn't try to do all, but in our paper, Dwork Crystals 3, there is some subset of these hypergeometric families. We didn't look on all 14. And speaking of the mirror map, there was a theorem about Dwork's families here. Let me show it. There was integrality of the mirror map already. Right?
Right.
Yeah, okay.
T, express T as a function of Q.
Okay, this part 1, yes, this is integrality of the mirror map already. But next time, so modulo the second step in our filtration, modulo F2, we get integrality of the mirror map. And with more sophisticated assumptions, we can get integrality of instanton numbers. Okay, that's good. That's good. And then this mirror modularity of mirror maps works for 14 families. That's we couldn't do. We tried that, but it's not true, right? They don't seem to be modular. Yes. Okay. All right. Not for all of them. Okay. Not all of them. Right? Yeah. All right. Okay. That's it. I look forward to your next talk. Thank you. Thank you.
Are there any other questions? Oh, if not, let's thank the speaker again.
Thanks, Soumya,
Thank you,
for
Masha.
chairing this session also.
Thank you.
And thanks, Masha. See you next time, the day after.
See you.
It was a really nice talk.
Pawan, are you stopped the recording and live stream?